Hello. So in this class, we shall be discussing Maxwell's equations. I'll have a separate video for each of the equation. This video will deal with the first equation. So what are Maxwell's equations used for? Maxwell's equations are used for electromagnetic waves. So Maxwell's equations are derived from the laws for electrical field and the laws for magnetic field. So we shall start with one law each. We shall proceed and see how it goes for each of the equation. So let me first start with Maxwell's first law. Let us go into the derivation first. So let us, what I am going to do today is, as I have already told you, Maxwell's first law for electromagnetic waves. So let me say I have a dielectric surface yes. Dielectric is like an insulator. It's an insulator actually. First surface is bounded by a volume V, meaning I am taking some object of a volume V. I am taking a surface S from it. Surface S bounded by a volume V, and I have the total charges as Q, and rho is the charge density. Okay, charges is Q and rho is the charge density. You will be starting with, in this case, Gauss law for electric field. For Maxwell's first law, we shall be starting with Gauss law for electric field, which states that surface integral of E dot ds is equal to Q by epsilon naught. Surface integral of E is the electric field, over a surface, a given area ds. So here this indicates it's a closed surface. So I am putting an S here indicating it is a surface integral, and this indicates it's a closed surface is equal to the charge divided by epsilon naught. You would have seen in school that epsilon naught is permittivity of free space. Epsilon naught is permittivity of free space. Now we see displacement vector D is generally given by epsilon into E, but epsilon is equal to epsilon naught into epsilon r. So I could write my displacement vector D is equal to epsilon naught epsilon r into E. But now our medium being air, you could say relative permittivity epsilon r is equal to 1, in which case my D now becomes epsilon naught into E. So I can now rewrite this equation as equal to surface integral epsilon naught E dot ds is equal to Q, which I can now rewrite as surface integral D dot ds is equal to Q. Now this is my first step. Now Q is the total charge is given as the charge density over a volume. Our charge density we just saw is given by rho. So Q is given by charge density over a volume over a closed volume. So now replacing Q with this one in that equation, I would be writing surface integral of D dot ds is equal to volume integral of rho dot dv. Now this particular equation is known as Maxwell's first equation in integral form. So which means we need to express Maxwell's first equation in differential form also. So this is the integral form. So for expressing in a differential form, what I am looking at is, I am looking at, now this is surface, this is volume. I am looking at some equality between these integrals. So I am going to convert this surface integral into a volume integral, for which I am now invoking Gauss divergence theorem. Gauss divergence theorem. Now I will tell you what divergence is. In the meanwhile, suppose I have a vector A. Now my Gauss divergence theorem states that the vector A over a surface S will be equal to a volume integral, the divergence of that same vector over a volume. Okay. So what is divergence? I have a point. The charges can radiate around from that point, or it can also converge to that point. So how well a point can radiate charges, how well my rays can diverge from a point, gives you divergence of a given vector. Now, when I have this, instead of A, I'm going to replace this D, which means I will have D dot ds over a surface will be equal to divergence of D over a volume. So I can replace this with this in this equation. So what will I have? Over a volume, divergence of D is equal to over a volume, the charge density. So if you look at this, both are over a volume with respect to a random volume dV. So I can now write del dot dV, divergence of D is equal to the charge density rho, which will give me Maxwell's first equation in a differential form. So we have seen Maxwell's first equation in a differential form and an integral form. In the next lecture, we shall be discussing Maxwell's second equation.